Learn like a pro.
All right, let's get into it. Today, we're cracking open the fundamental blueprint for how electricity works, the series circuit. It might be the simplest way to hook things up, but its rules are super strict, incredibly powerful, and, well, they explain a very common headache. You know the drill, right? We've all been there. You wrestle that tangled mess of old holiday lights out of the box, you plug them in, and zip, nothing. All because one tiny little bulb decided to give up. Well, that exact frustration is what we're explaining today, because the answer is locked inside the simple, unbreakable laws of a series circuit.
So, to really get why this happens, we need to zoom way, way in. We're going to start in the invisible world of current to see how these electrical charges actually behave. And this right here, this is the golden rule, the most important principle of a series circuit. There is only one path. Just think of it like a single-lane highway with absolutely no exits. Every single one of these little blue spheres, our electrical charges, has to follow the exact same route. No detours, no passing. That one simple fact changes everything. Okay, so we've got our single path. Now let's look at what's governing the traffic on this one-way street. Turns out there are two fundamental, unbreakable laws that everything here has to follow. Law number one is all about the flow, which we call current. And in a series circuit, it's a constant. It's the same everywhere. See the gauges here? They all read 1.0 amp. It doesn't matter if you measure at the beginning, the middle, or the end, the rate of flow is identical at every single point along the highway. But this is where things get interesting. Law number two is about potential difference or voltage. You can think of voltage as the energy or the push that the source provides. Now, unlike the current, this energy gets used up. The red bars here show you how the total voltage from the battery gets spent or dropped in little chunks across each part it passes through. So let's nail this down, because it's the key difference. The current, that's the flow, stays the same all the way around. But the potential difference, the energy, gets divided up. If you add up all those little individual voltage drops across the components, they have to equal the total voltage that the battery started with. The energy budget has to balance. All right, so we have the path and we have the laws of flow. But what's actually controlling that flow? This brings us to what gives the whole circuit its unique identity, its signature, if you will, its total resistance. We call this the effective resistance. It's basically the grand total opposition to the flow. It's the overall bottleneck that the current has to squeeze through. And the best part? In a series circuit, finding it is incredibly simple. You just add up all the individual resistances. That's it. This visual makes it super clear. As far as the power source is concerned, it doesn't see two separate obstacles of 4 ohms and 8 ohms. No, it sees one single combined bottleneck of 12 ohms that it has to push against. So now we've got our 3 key players: voltage in red, current in blue, and resistance in orange. And the master key, the magic formula that ties them all together, is Ohm's law. Voltage equals current times resistance. With this little toolkit, we can figure out pretty much anything about a series circuit. Okay, theory's great, but let's see this in action. It's time to put on our detective hats, because we're going to use these rules to solve a little mystery in a circuit diagram. Here's our case. We've got a 9-volt battery hooked up to 2 resistors. We pull out our meter and measure the voltage drop across that first one, and it's using 3 volts. So the question is, how much voltage is left for the second resistor to use? So how do we crack this? Well, the logic is actually really straightforward. First, we just remember law number 2. The total voltage is just the sum of the individual drops. Second, we just do a little algebra to solve for our unknown, V2. And finally, we just plug in the numbers we already know. And boom, there's our answer. We started with 9 volts total. The first resistor used up 3 volts. That leaves exactly 6 volts for the second one. The puzzle is solved and our energy budget balances perfectly. See? Simple. And you know what? We can even take this one step further and find the current for the whole system. Using our master key, Ohm's law, we just divide the total voltage, 9 volts, by the total resistance we found earlier, 12 ohms. That tells us we have a current of 0.75 amps flowing through the entire circuit. Now, this all seems pretty neat, tidy, and predictable. But this super simple design comes with one huge drawback. A real Achilles heel that brings us right back to those frustrating holiday lights. Because there is only one path. A single break anywhere in that loop brings the whole thing to a grinding halt.
It doesn't matter where it happens. A burnt-out bulb, a snipped wire. It's like a bridge being out on our single-lane highway. The road is closed. The flow of charges stops instantly, everywhere. Game over.
And that brings us to the final, really important question. If series circuits are this fragile, if they have this built-in self-destruct button, why on earth would we ever use them? What possible advantage could this single point of failure have? The answer to that? Well, that's a story for another time.